Okay. Just as a review, now this is chapter 10 stuff. Now this test is going to involve, test 2 is going to involve chapters 9 and 10, different chapters. And the order by which I go through is going to be based on the requirements for 1A. Okay, as a review, carbon, for example, has typically 6 electrons. Okay, some of those are core electrons and some of them are valence electrons. Valence electrons, again, are the outermost electrons. That is where all the chemistry takes place. The core electrons are not affected at all in terms of chemistry. The reason for that is they're super stable. Now, from yesterday, I mentioned reactions start with something unstable and goes to something stable. So if it's already super stable, nothing's going to happen. But those valence electrons, those electrons in the outer orbital, are not stable. They want to do something. They either want to combine with other electrons or they want to leave the atom totally and become an ion. So back 150-ish years ago, we had this issue. Okay, chemists at that time could create a formula. Say like that. The problem is we didn't know what the structure of that looked like. So Dr. Lewis took the valence concept, the valence electron concept, and came up with some rules to put together structures. Now, we're going to do a lot of Lewis structures in here. We're going to do fairly straightforward ones, though. Lewis structures can get quite sophisticated. That's for 1A. But I want you to go into 1A or 2A knowing the basics of Lewis structures. Because if you have to start from zero and get into the sophisticated structures, you'll die. So anyway, all right. So what he did was he put together some of the most common chemicals that we're going to run across. And what these dots represent are valence electrons. So boron, if you look where boron is, boron's got 5 electrons. How many core electrons does boron have? 2. How many valence then? 3. 2 plus 3 is 5. Okay. We're not dealing with core electrons again, just valence. So boron's got 3. Carbon's got 4. Nitrogen has 3. Now, notice I didn't say 5, I said 3, because we're looking at the singleton electrons, not the pairs. So once we get above 4 valence electrons, electrons start pairing up. And we'll talk about why they're pairing up. But for now, nitrogen's got 1 pair, 3 singletons. Oxygen has 6 valence electrons, 2 pairs, and then 2 singletons. Okay, so we need to define a bond. Let's see. Okay, there's 2 main types of bonds we're going to cover in this class: ionic bonds and covalent bond. A covalent bond is a sharing of 2 single electrons to form a pair. Okay, so the pair is a bond. Now it's got to be on 2 different atoms to be a bond. It can't bond to itself. All right. So Lewis structures involve both ionic and covalent. We're going to focus on covalent in here. All right, so having just given you the definition of a covalent bond, how many bonds can hydrogen make? Ask yourself, how many singletons does it have? 1, so it's going to make 1 bond. What about boron? 3, carbon, 4, nitrogen, 3, 2, 1. Okay. Now there's a concept that we're going to talk about a little later. It's called an octet. When an atom has its own valence electrons plus shared electrons, if it totals 8, it's said it's being in an octet. That is very stable, an octet. So now the only exception to that is boron and hydrogen. Hydrogen can have more than 2 electrons. So hydrogen is the exception to what I just said. Now, multiple bonds. You can have a single bond, a double bond, triple bond. When I say the word bond, I want you to think of 2 singletons paired up. So if carbon has a triple bond, it's got 3 bonds of 2. So that's 6 total electrons that are shared with another atom. I'm going to be doing lots and lots of examples. So carbon has to have 4 bonds, and it can be a combination of one single and one triple, two doubles, four singles, long as it adds up to four. Now I'm going to talk about in a few minutes concept of a legal Lewis structure. To be a legal Lewis structure, two things have to happen. The number of bonds have to be correct, and each atom except hydrogen has to have 8 electrons or an octet. Then it's a legal Lewis structure. Okay. So these are the rules to go by. Say we have CH4, methane. All right, number one, when we want to do a Lewis structure, now one of the challenges of Lewis structures are they're two-dimensional. Life is not two-dimensional. Life is three-dimensional. Okay, so the rules are I'm going to type this instead of printing it out here. Okay, and number 4 and 5 determine whether the structure is legal or not. Now, this is a document in files. If you don't want to write all that. Okay. So let's do some examples now here. let's do, okay. So we've got carbons and hydrogens there. Which has the most singleton, the carbon or the hydrogen? Carbon. So that goes in the middle. And the rest of the hydrogens, we're going to spread around the carbon. Okay, so that's number one. Atom with the most singletons goes in the middle. Then everything else kind of surrounds that. Now, there are two atoms, hydrogen and fluoride, just say fluorine, not fluoride, have only a single singleton. Those always go around the outside. They're never in the middle, unless you just have like F2 or H2. But normally those surround the center atom with all the singletons. Okay, so step number 2 is connect all the atoms with one bond pairing up two singletons. By the way, this procedure differs from your book. Your textbook is a much more complicated process to do this. Okay, so that's step number 2. Step number 3 is check for lone singletons. Do we have any non-bonded singletons? Everything's bonded up, right? Okay, so number 4, check for legal number of bonds per atom. How many bonds does carbon want? 4. And how many bonds does carbon have here? 4. So that's good. What about hydrogen? How many bonds does hydrogen want? 1. And each hydrogen has 1 bond. Check for octet per atom except for hydrogen. Hydrogen needs 2. So it's sharing 2 electrons for each one. Carbon needs an octet, 8. Each bond has got 2, so 2, 4, 6, 8. So steps 4 and 5 are met. That means that's a legal structure, Lewis structure. The next thing is you take the dots and convert them to lines. Okay, so that's a Lewis dot structure for methane. Okay, so any questions about this guy? Again, that's about the simplest Lewis structure you can have. So I'm going to erase this because I want to keep the rules and everything on the left there. Okay, before I erase it, okay, so let's do another one. This is called formaldehyde, by the way. Who's heard of embalming fluid? Formaldehyde. When you preserve anything in a jar, formaldehyde. Formaldehyde is not nice for humans. What it does, if you start breathing this, it will embalm your esophagus, parts of your mouth. So frequently they'll dilute it with water, and then it's called formalin, but it's still formaldehyde. So whenever you get into anatomy, physiology, zoology, any of those departments that have preserved things, whether it be an organ, animal, whatever, you're going to be around formaldehyde. Be aware it's not good for you, period. Not good for you. All right, so that's formaldehyde. What's the structure look like? Well, here we got carbon, hydrogen, oxygen. Which is the most, has the most singletons in it? Carbon. Hydrogens, as I said before, we're going to put around the outside. Notice I didn't say where, I just said the outside. Now we can move stuff around for convenience. And then we have oxygen. Now with oxygen, it's got two singletons and two pairs. It's better to put the singletons towards the carbon for convenience, and the pairs on the outside. Okay, so that's step number one. Step number two is connect the dots. Each atom has to be connected at least once. Okay, so the carbon has made a bond to oxygen and the two hydrogens. Number three, check for any lone singletons. Are there any singletons left over unbonded? There are, so we have to connect those up. Now, a lone electron by itself is called a free radical. Those are very, very unstable. And because they want to seek stability, what they do is they bond with something immediately to become more stable. Now, in atomic bombs, you create a lot of different things. One of the things you create are free radicals. And one of the problems with free radicals, if they happen to be around vital organs, they're going to bond with that vital organ, and you get radiation sickness. That's one of the things from radiation sickness. So free radicals, because they're so unstable, they need to be bound up. Can't have any lone ones just running around. So we've got two singletons. We need to bind those up. Okay, so now there are no unbound singletons. Now, this is kind of weird looking. So let's dress this up and make it a little more symmetrical, because you can move the locations of those singleton electrons and the pairs around anywhere you want. But you can't undo the paired electrons. They have to stay paired. It means they don't bond with anything. Now, there's a special circumstance where they can bond. We're not going to talk about that. Okay, as far as we're concerned, the pairs don't bond. So let's move stuff around so it looks prettier. So I still have the same connections. There's a carbon-oxygen double bond, and there's a single bond between all the hydrogens and the carbon. And we have no singletons left over. All right, check for legal number of bonds per atom. Okay, carbon needs 4 bonds. How many bonds does carbon have? Got a double bond and 2 singles. 2 plus 1 plus 1 is 4, so that's legal. The hydrogens need one bond apiece, and each one has, so what about oxygen? How many bonds does oxygen need? 2, because it has 2 singletons. Oxygen's got a double bond with carbon, so it's got 2 bonds. So that part's legal. So step 4 is done. Octet. Let's look at oxygen first. Oxygen's got 2 bonds, that's 4 electrons, and 2 pairs, that's 2 apiece, so that's 4 more. So oxygen has octet, 8. Carbon's got 2, 4, 6, 8. Hydrogens have 2 apiece. So that's step 5 is legal. We have the octet rule met. Now we connect all the bonds with single lines. So that's what formaldehyde looks like. Now, what's nice is you can move these electrons around so your structure doesn't look weird. Move it around and things look a little nicer, more straightforward to put together. Also, keep in mind that atoms can tumble in space. So sometimes I'm going to give you a lot of worksheets to do Lewis structures on to practice. And sometimes my structure may look different than yours, but yours may be perfectly legal. For example, if my answer looked like this, that's the same structure. Okay, things can rotate in free space. Also, there can be alternative structures with the same formula. Okay, so before I go on to another one, any questions about this guy? Okay, C2H6O. Now this is going to have 2 legal structures. One's called drinking alcohol ethanol, the other one's called dimethyl ether. Dimethyl ether used to be used as an anesthesia. When I was 4 years old, I had my tonsils out in 1954. And this is what I remember. I was lying down on the operating table, and the anesthesiologist, I assume, 4 years old, I don't remember, had a little stainless steel screen like this with cotton on it, and she poured dimethyl ether onto that. And then this is what I remember, coming down like this, and then waking up with a sore throat. They took out my tonsils. Didn't remember a thing. They don't use ether anymore. They have a lot better stuff. But in those days, that's how I remembered it. Gangsters would kidnap people. Take a handkerchief, put ether on it or chloroform, come behind you, down you go. So there's a lot of organic chemicals that are used for anesthesia that have been used for a long, long time. Chloroform is a bad reason I know what chloroform smells like. I was in graduate school. I was doing a month-long ion column extraction. Chloroform was the solvent. And every 2 hours, I had to check it 24/7. So I was in the lab like 3 o'clock in the morning, 1 o'clock in the morning, all the time. Sometimes I would sleep there. It was a pain, but it had to be done. And graduate students are cheap labor. That's the way it is. So I used to drink a lot of coffee. And when it was dark and no one was in the building, I used to cheat and bring my coffee into the lab. I had a beaker of chloroform about this big. My coffee cup was about this big. And I was sleepier than you know what. So coffee cup extraction, coffee and drinking. Beaker chloroform, thinking it was my coffee. And unfortunately, I got it up to here, and the fumes I could smell. Chloroform is very sweet smelling, very weird. And I all of a sudden realized what was going on. I put it down and went, holy. I can just see my lab mates coming in the next morning with me on the floor, you know, kind of flopping around. So anyway. I don't know. I don't know how documented it is, ingestion of chloroform, because no one does that. Yeah. Yeah. So, man, it was. So it's like, do as I say, not as I have done. So, yeah. Used in what? Yes. It's very combustible. And there's different kinds of ethers. Ether is a carbon-oxygen carbon bond. So you can have stuff on either side of the oxygen. Because in fact, my 306 class, which is 2B over in Sac City, we're just on ethers last week talking about those. Yeah, ethers are super. In fact, one of the problems with in the lab, if you have diethyl ether, which instead of a single carbon on each side of the oxygen, you have 2 carbons. That's used as a solvent a lot. And one of the problems is old ether creates these crystals around the lip of the jar or can, depending on how you have it stored. And they are extremely explosive, form something called picric acid. And many labs have had explosions in them because of their old ether. And it's very combustible. They use it as a fuel alternative in competition cars and stuff. Is that how you know about it? Yeah, who's heard of starting fluid? What you use, right? Yeah, starting fluid is ether also, and you spray it into your intake of your engine. I had a farm too, and and some of the engines only was starting with starting fluid. Stuff works really well. If you have a lawnmower you haven't used, you know, like in the spring, you haven't used it all winter, just buy some of this stuff. It really works well. And you just spray it right into the air cleaner, and your lawnmower will start right up. I mean, one pull, it'll start right up. Works really well. And then after that, I'll blow out all the cobwebs and everything else. So yeah, we had on our farm too. We had lots of starting fluid. All right, so let's deal with this. Now, this is again, it's going to be 2 legal structures. One's going to be dimethyl ether, and the other is going to be ethanol, which is drinking alcohol. Okay, so we've got carbon, hydrogen, oxygen. Which has the most singletons of those 3? Carbon. So I'm going to put those in the middle. And then we have an oxygen. And we have 6 hydrogens. Okay. Rule number 2, connect all the atoms together with one bond. Okay. Are there any lone singletons? No lone singletons. Okay. All right. Check for legal number of bonds. Carbon needs 4 bonds. The middle 2 carbons each have 4 bonds. Oxygen needs 2. Got 2. Octet wise, carbon needs 8, 2, 4, 6, 8, 2, 4, 6, 8. Oxygen needs 8 also. So we have 2 bonds, 2, 4, and 2 pairs. 4, 6, 8. So we have 8 electrons there as well. So 4 and 5 are met, hence it's a legal structure. Now we're just going to and notice I took these guys and just kind of moved them outward, convenience-wise. Okay, so that's ethanol. Ethanol is a 2-carbon alcohol. Now, alcohol, there's rubbing alcohol, there's drinking alcohol, there's methanol, there's propanol, there's lots and lots and lots of alcohols. Biologically, there are even more. There are tons. Cholesterol is a fancy alcohol. Carbohydrates are alcohols. Sometimes they're called polyols. Lots and lots and lots of alcohols in your body, biochemical. So it's a very common type of molecule. All right, does everyone see how we got that structure? Okay, now we're going to do an alternate structure. Let's do that over here. Okay, so carbon, again, you already mentioned it has 4 singletons, so it goes in the center. But we're going to position the oxygen, though, between the 2 carbons in this case. Let's move this over here. Okay. So it's not a steadfast rule that you put the atoms with the most singletons in the middle, just approximately in the middle. But that'll be your first shot out of the gate, is to put them there. And afterwards, you can start moving things around a little bit. Okay, so we need to connect up everything. Step number 2 is connect everything up once. Okay, do we have any lone singletons? No, we don't. So let's check for number of bonds. How many bonds does carbon need? 4. 1, 2, 3, 4. Oxygen needs 2 bonds there. Carbon on the right, 1, 2, 3, 4. Hydrogens are all single. So that's legal as far as number of bonds goes, octet wise. Left carbon 2, 4, 6, 8. Right carbon 2, 4, 6, 8. Oxygen in the middle has got 2 bonds. That's 4. and 2 pairs, that's 4 more, so that's 8. So 4 and 5 are legal. That means this is also a legal structure. Now, on a test, if I gave you C2H6O and said write a structure, and you put one of the 2 down, that would be fine. Legal. Now, I might say draw 2 structures for this formula. Then you need to do 2 unique structures. Yeah. By looking at the picture? Okay, so right here, 1 bond, 1 bond, 1 bond, 1 bond. So did they answer your question? No, I was asking her. I said, did they answer your question? Okay. Okay, her question was, how are you counting up bonds? Okay, a bond, remember, is 2 singletons shared. So every time I circle that, that's a bond because you're sharing those 2 singleton electrons. Yeah. No. And the reason why it's not the same thing is if you go by that, carbon should only have 2 singletons. Carbon's got 4. And the reason for that is out of the scope of this class, but it's called bond hybridization. And that's why it's not 2 singletons. See, carbon should have looks similar to oxygen. Okay, so counting up bonds, you're looking at those circled pair of singletons. How many of those are attached to carbon? We've got 4 there, where the yellows are. For the oxygen, we have 2 bonds there. And notice I'm double counting them when I go to the adjacent atom over, because we're sharing those electrons. That's why you're double counting them. Then we go over to the right-hand carbon, 4 bonds there. Okay. So that's a legal structure. So now let's go ahead and put in solid lines for the pairs of singletons. That's dimethyl ether. All right, so I'm going to give you a structure, and I want you to, on your own now. Are there any questions about either one of these? You're just hooking up the singles. Out of that chart, this chart. Look at carbon up there. How many singletons does it have? Yeah. 1, 2, 3, 4. 4, exactly. It has to do with how many valence electrons carbon has. No. A week ago or so, I told you how to figure out valence electrons. You count on the row that the element is on. So look at carbon on the second row down on the right. So count from left to right how many boxes carbon has to get to. Count from left to right. How many is that? 4. That's where the 4 comes from. Okay. Notice nitrogen is okay. Now, those numbers you were referring to, the 3A and the 4A, that says how many valence electrons, not necessarily how they're paired up or not. Because you look at nitrogen, how many valence electrons does nitrogen have? 1 more than carbon, so it's got 5, right? But see, 2 of those are paired up. And you wouldn't know that by looking at the 5. That's why you need to use this chart. Okay, so the A numbers tell you how many valence, or you can just count left to right. So nitrogen is 5 over, oxygen 6 over, fluorine is 7 over, and then good old neon is 8 over. You don't count the boxes above because those are core electrons. Yeah. And see the 7, how does that come up with 1? And see the 7, that's why you just need to know. You need to know that, but you're going to have enough practice that you don't need to memorize it. Keep it handy in the beginning though. All right, so we're going to finish today with you guys doing one totally on your own. Okay. Go ahead and do that one on your own. That's called acetic acid. And there are 6 versions that are legal for this formula, by the way. So your neighbors may have a different structure than you that's totally legal. Just making sense.
Kind of. I thought I answered my own question, but then I'm looking here and I'm like, okay, so C has 4 singletons. That's kind of what I started going off of. But
Right.
then oxygen.
That's
has-
2.
Okay, so because the way it was drawn, I thought they were together, so I separated them and then it started to make sense. Like I can do it like that, right?
Yeah.
Okay.
You can move the singletons and pairs any way you want.
Anyway, okay. But it is confusing at first because you can move them around. So most of the C's. Oh, gosh, that. Okay, dots, right?
Yeah, stick with the dots for now. When you're an old hand at this, you can.
Right, when I get better at it.
Or when you put your elements down, don't connect anything in. Just put the total number. Yeah. And draw your pairs not like that, but more parallel to the curve of the O. And the way you drew them here. See, they're not like this. They're kind of like they're in an orbital around the oxygen.
Yeah.
That's not what I meant.
Okay,
You're stabbing the teacher here,
I'm sorry.
like this.
Oh, around like that.
Yeah. And you can stick the singleton over here or over here. Let's just stick it here. Yeah. Remember, you can move those around.
Closer.
And make the pairs, obviously they're pairs. In other words, put them real close together. Yeah, like that. You're on your way. Let me see here. No, see, you didn't connect up all the atoms together. See, you have those connected up, and these, they have to be all connected together.
Yeah, that's what I. Would that be better?
Hey, yeah, there's 6 versions of this that are fine, so. As long as the rules are number bonds and the octets. As long as you fulfill those, it's a legal structure. It doesn't matter if it's cyclic, if it's linear, it doesn't matter.
That'd be right. I know. It's-
Yes, it is small. All right, let's see here. No, see, you've got the hydrogens by themselves.
Mhm.
They have to, everything has to connect together.
Okay.
So, what's nice with a big eraser, you can erase that.
Yeah.
And see, you've got 2 singletons there in that oxygen. Remember, you can't have lone singletons. So keep the pairs together on the oxygens. And you're missing 2 electrons in each one. So the oxygen has pair there, and a pair there.
Mhm.
Keep them together.
Okay.
And draw bigger. You got all this paper. Okay. You got a good start, except you got a single in there with nothing bonded to it.
That only does one of them.
Yeah, okay.
So
So the only way it can happen is if it's can bond with a singleton. Um, let's see. You got a cyclic structure going here, which is fine. What's wrong with this now? We need a singleton here somewhere. These 3, yeah, the formula is right.
these need a bond together. These need a bond together. These need a bond together. Does that have to be the case? Or?
No, there's different combos. There's like 6 versions of it. This is one of them, though.
Oh. Maybe is it supposed to be one there? That bond with the hydrogen? 1, 2, 3, 4.
Oh, yeah.
Okay. Okay.
So what I'd suggest, instead of, let's erase that one there. And
On these and then put the
Yeah,
hydrogen.
exactly.
Okay,
Exactly.
gotcha. Thank you.
Yeah, I was trying to figure out, where's the,
Yeah, it was a little messy to figure out. Yeah.
Yeah.
All right,
Yeah.
Thank you.
so 2 bonds, 2 bonds, 4 bonds, or legal.
Okay.
And then count octets. Yeah, 8 there, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, so it's legal. Now put in lines for these guys.
Okay.
Yeah, I think you're in a That work?
Kind of figure.
This is tricky. This is the trickiest one we've done so far. You can connect up any combination of singletons. And just make sure every atom is connected to kind of together. Don't make two molecules out of it. Let's see here. Yeah, that works. Good. Come up with another one now. Remember, there's 6 of these that are legal. Yep, that's what he did down there. Exactly like that.
Yeah.
Good. So come up with another one. And this is the one that most people don't know about because it's cyclic. It doesn't matter. It can be cyclic, it can be, you know,
Yeah.
whatever, as long as you go with the rules. Now, did you follow me okay when I was doing it? Okay, so why don't we back up then? And destroy your notebook here. And do one of these that I, okay, do a, instead of that one, let's do a simpler one. Let's do, you see,
don't get the one.
singleton, it can hook up, kind of like at a bar. Two singles. Mhm. And then you circle it, just so that you recognize it's a bond.
Okay. Oh, that's what we do in this book.
So try this one here first. How are you doing?
I'm gonna see
Is making sense? Just need to practice 29,000 of them. Okay,
kind of messed up on the placement of the buttons.
now you've got to, so you ended up with 2 molecules. This is 1 molecule. So the bonds are going to be between the 2 here. Okay, so, you have no connection between the 2 carbons, so you need a connection there.
So they should.
Yeah, this is 1 molecule. So that means everything's got to have at least 1 bond connecting them up. Yeah.
Okay.
Yeah, for example, you can go like this. That connects up the carbons. And oxygen has 2 singletons. You wrote it as 3 pairs. It doesn't have 3 pairs. It has 2 pairs and 2 singletons. So let's do this differently here.
So how do you know that it's 3 instead of 2?
From your notes here. This here.
So even though
See, these 2 are a pair.
Sure.
These 2 are a pair. Then you have 1 here. You could write it over here too. Let's write it over there instead. That way, so it doesn't appear like there's 3 pairs. So, yeah. Okay, so you might want to just rewrite this because it's hard to,
see everything.
well,
Isn't it still 5 though?
Hmm?
Isn't it still 5?
no, it's supposed to have 6.
Okay, 3. You said 3 pairs.
Fluorine has 3 pairs,
Okay.
the next one over.
Okay.
Oxygen has 2 pairs, Nitrogen has one pair, oxygen has no pairs. Okay, so forget this. Just start connecting up to singletons.
Okay.
You may have to move hydrogens around too. You might move a hydrogen up here to connect to that one. Another hydrogen up here.
Thank you.
Main thing is though, get the oxygens right though. Two singles, two pairs. That means oxygen can have two bonds.
That makes more sense now. Okay.
Okay, try it again. Do you have lab today?
Yes.
Okay, so in lab, you might want to make sure that you have this down before you leave today. Yep, that works fine. There's 5 more.
Okay, 5 more.
Yeah, that are legal.
Yeah.
Yeah. A lot of people have been doing circular one. The other way is to put the oxygens connected to them to each other.
Mhm.
So you end up with carbon, carbon, oxygen, oxygen,
Okay,
and then that's.
Yeah.
Or you can just put them in a long string. I mean,
yeah,
all these variations and inversions and all that. That's good though. And it makes sense that process.
yeah. And there would be 8 bonds. Correct?
Huh?
There would be 8 bonds.
Well, carbon needs 4. There's 2 of them, that's 8. Oxygen,
Okay,
2 apiece, that's 12.
12.
And then
okay,
all the hydrogens.
so that's 16.
Let's see now here.
Yeah. That works.
Only, that's correct, but not this.
That's
So you've got carbon oxygen has 2 bonds, not 1.
Mhm.
You just have 1 there. And another bond there. Right here. So you've got bond, bond,
yeah.
bond. Bond,
Oh, okay. Yeah, because I connected it twice.
twice, right. So
Okay,
that's
so
got to
I
be
just need
reflected
2
in your
lines.
line. Yeah, exactly.
Okay.
Okay. Yeah, that's good. And there's 5 more versions that are legal. So. Did you get the same one as her?
She needs help.
And for my spectral off.
That's why I screwed it. I probably shouldn't.
That's fine. Yeah.
Like, I don't know how to check for the legal limit or whatever.
Carbon needs 4 bonds. 1, 2, 3, 4. 1, 2, 3, 4. Oxygen needs 2. 1, 2, 1, 2. Later in the course, I'm going to show you where that comes from. The problem is carbon is the exception. Other than carbon, I can show you exactly how it falls out. Just count the pairs,
Okay.
the pairs and the bonds. Each bond has 2 and each pair has 2.
Okay.
Count by 2s up to 8. You have to have both of them met, not just one of the 2. Okay, so.
Garbage.
Okay, so you've got, we're almost there. Here's your pen.
Yes.
Let's carbon back in. And so you got that and that and that, right?
Yes.
You got this lone.
Air from hydrogen.
Mhm. So you've got a lone one here as well, right?
Yes.
Okay, so instead of connecting here, let's connect like that and move this one over here. And then these guys are going to connect up with that. you've got. You've got,
What I was thinking.
well, you're almost there.
Okay. I didn't put them in the,
So this here are these.
Yeah.
You have the CH, and then you have two bonds connecting the carbons. 'Cause you have some loners out there, and these need some companionship.
Mhm.
So that's,
That helps. This one right too. Or is that?
Yeah. yeah, that's what she's got here. Yeah, that works fine. Yeah, that's what she's got. Oh, yeah, that works fine.
Yeah.
Yeah, this is a special reaction. This is called an enol in organic chemistry, and that's how fructose and glucose connect. One gets converted to the other and vice versa. That's how they make high fructose corn syrup. Yeah, so you got it. It was a little hard to follow with your,
One doodle.
yes. Look at hers. Very clear. So which one do you want me to look at?
Yep, you've already checked.
Oh, okay. I thought you were showing it to me. You want to check another one? Oh, you
Are we doing another one?
no, it's time to go. All right, everyone. I'm going to post some worksheets on practicing Lewis structures. Okay, now when you go to 1A or 2A, they're going to expect that you know this already. So star, real important. Okay. All right, I'll see Saturday lab folks in a little while. I've got to convert the file and blah blah blah.